The author's project with the titles Turn on Common Sense presents the movie, Experiment, Measuring the One-Way Speed of Light. I would like to draw your attention to the fact that in the description of the video there are time codes, by which you can review what you find important or interesting. Introduction. The purpose of this video is to describe the idea and scheme of realization of the experiment, which will allow to reveal what is light. It is either some wave in a light-bearing environment, or something else, which corresponds to the mathematical formalism of the special theory of relativity. For several years there has been a technical and technological possibility of such an experiment. Now in the scientific community it is considered that the speed of light in vacuum does not depend on the direction of its propagation, and even the length of a meter is determined by the speed of light and a second of time. However, until now there has been no convincing experiment that measures the unidirectional speed of light separately in one direction and in the other direction. An experiment that will reveal the unidirectional speed of light is exactly what is proposed in this video. This experiment addresses what the well-known experiment called the Michelson-Morley experiment failed to do. Let's take a closer look at it. Michelson-Morley experiment. Light and electromagnetic waves are wave oscillations. But what are these oscillations? That's what the scientists of the second half of the 19th century wanted to find out. They called this light-bearing environment the ether. It was assumed that everything is in this light-bearing environment and moves in it. At least our planet Earth should move in this ether in its movement around the Sun. This relative motion is indicated by the annual aberration of the stars. However, it was not possible to detect absolute motion relative to this environment in numerous laboratory experiments with electrical, magnetic, and light phenomena. Michelson invented a setup, the Michelson interferometer, which had a very high sensitivity, so he could already detect the second-order effects of smallness implied by motion in this environment, the ether. Michelson conducted many different experiments, so his repeated experiment with Morley to detect velocity in the ether with even greater sensitivity is called the Michelson-Morley experiment, actually indicating the type of experiment. This experiment and its repetition by other scientists with ever-increasing accuracy did not reveal the expected effect. This was explained by the fact that bodies contract longitudinally relative to the motion in this environment, which later became known as Lorentz contraction. Albert Einstein went, we can say, a more radical way, or, to be more precise, a way in the spirit of Mach's philosophy. The meaning of this philosophy is quite simple: if we cannot find the cause of a phenomenon, there is no need to look for this cause, but we should take this phenomenon as a given of nature and it will be enough to describe this phenomenon mathematically. If this mathematical description is made correctly, then correct conclusions will follow from it, and confirmation of these conclusions will allow to confirm, clarify, or refute the proposed mathematical dependencies. A clear example of such an approach before Mach and Einstein was Newton's law of gravitation, which not only united three unrelated laws of Kepler into one dependence, but also from this Newton's law there followed consequences in the form of the existence of parabolic and hyperbolic orbits. Returning to the Michelson-Morley experiment and using the above statement of Mach's philosophy, we can say affirmatively that the negative results of this experiment are a law of nature, which is reliably experimentally confirmed. And how can this law of nature be described mathematically? Einstein proposed, let's assume that the speed of light back and forth does not depend on the direction of its propagation in space. This agrees well with the Michelson-Morley experiment. But it seems to be insufficient, as there is no difference in all experiments when the Earth moves in one direction relative to the stars, and half a year later, in the other. So we can assume that all inertial systems are equal. Here you have both postulates of the special theory of relativity. Further, purely mathematically, the dependencies of the special theory of relativity are obtained, including the reduction of Lorentz bodies. Thus this reduction is not some miracle, and it is laid down initially postulates. But this reduction of bodies is now called by another name, Lorentz transformation, and it already refers not to bodies, but to space. This is how I vulgarly, but briefly and popularly showed the essence of the crisis in physics at the end of the 19th century and the essence of the theory of relativity. This approach, proposed by Mach and realized by Einstein, to the solution of scientific problems turned out to be not so harmless and progressive as Newton's law for gravitation, because very dubious conclusions followed from it. The main conclusion, which significantly affects the development of physics and related sciences, is that the physical vacuum is a void. That is, the presence of any environment between bodies is denied. Denial of any environment between bodies follows from the fact that in the presence of environment, inertial systems would be unequal with respect to this environment and among themselves. The presence of an environment implies some speed of light relative to this environment, so for different inertial systems the speed of light would be different. That is, both postulates of the special theory of relativity together and separately are not compatible with the presence of some environment between bodies, molecules, atoms, and even particles in atoms. In addition to the presence of questionable conclusions, the special theory of relativity was internally contradictory because it made conclusions that contradict each other. Formally, if to follow logic, the special theory of relativity should have been discarded because of internal contradiction, but it did not happen. It did not happen because of the substitution of concepts. Instead of the obvious logical concept of contradiction applied a softer and ambiguous concept, paradox. That is, it is already as if not a contradiction, and one more riddle of nature, and consequently the special theory of relativity can be considered true. About paradoxes of the special theory of relativity you can learn from the video, which are linked in the description. As for the special theory of relativity in general, given that it operates with such concepts as space and time, which, as we know from previous publications and videos, links also in the description, are abstract concepts and do not exist outside our consciousness, this so-called theory has nothing to do with objective reality. That is, manipulation of these concepts in the form of compression or curvature of space and changing the rate of the clock depending on the relative speed is essentially a process of guessing the behavior of objective reality and no more. From this we can conclude that even if the special theory of relativity would not have internal contradictions, then even in this case it cannot be considered a theory, because it operates with concepts that do not exist outside our consciousness. After some digression, let us return to the Michelson-Morley experiment and the contraction of bodies. The contraction of bodies is not some convenient dependence to explain the negative results of this experiment, assuming the contraction of bodies in the longitudinal direction to motion, but it is an ordinary physical phenomenon, similar, for example, to such phenomenon as magnetostriction. This contraction of bodies depending on velocity relative to the environment is logically and mathematically deduced, with the contraction of bodies occurring in all directions relative to velocity, but by different amounts. You will find a link to the description of the idea and the derivation of the formulas in the description of the video. Why is it written about the Michelson-Morley experiment, the special theory of relativity and the physical contraction of bodies? And to the fact that the results of the Michelson-Morley experiment are simply explained by an ordinary physical phenomenon, although it is difficult to detect it experimentally, but still there is no need to resort to such mathematical twists that are present in the special theory of relativity. And the consequences of this theory lead to such monsters as the Big Bang theory, dark matter, dark energy, and others. Many see the logical shortcomings of the theory of relativity, do not agree with it, but only a properly conducted experiment, aimed at verifying the consequences of theories, can bring clarity to various theoretical reasoning. One such experiment to reveal the motion of the experimental setup relative to the environment was previously proposed in the video and on the website. You will find a link to them in the description of this video. Another type of experiment to detect motion relative to the environment and determine the one-way speed of light is outlined in this video. This experiment is based on synchronization of clocks separated on some distance and observation of the course of these clocks in the process of their mutual rotation. By mutual rotation we mean the rotation of the supposed line connecting these clocks relative to the conditionally stationary stars. Idea of the experiment. The idea of the proposed experiment is as follows. We place two very accurate clocks at a sufficiently large distance from each other, which is constant in magnitude or close to it. Another condition of the experiment is that the objects on which these clocks are located move relative to each other so that the conditional line connecting them is rotated so relative to the distant stars that the plane of rotation of these objects coincides with the expected velocity of motion of the objects and the clocks together with them relative to the expected environment. That is, the clocks rotate relative to each other in the plane lying on the vector of the expected velocity in the environment. This experiment, unlike the Michelson-Morley experiment, is an experiment of the first order of the ratio of the expected velocity in the environment to the speed of light, so it has a significantly greater effect than the Michelson-Morley experiment. After synchronization of clocks by means of radio signals, which, presumably, propagate in the environment, it will be possible to determine the difference in the clock rate, since the time of arrival of radio signals from one clock to another when they propagate along the velocity in the environment will be later, since the clock runs away from this radio signal, and when they propagate towards the velocity in the environment, the radio signal will arrive earlier, since the clock runs into it. In the process of rotation of clocks relative to each other, the readings of clocks at the time of arrival of the radio signal will periodically differ from each other, since then one clock will run away from the signal and the other will run into the signal, and then vice versa. The results of the experiment depend on the accuracy of maintaining the stability of the parameters and the method of clock synchronization. Synchronization of clocks. Determination of the one-way speed of light can be made by synchronizing clocks separated by some distance, and it is desirable that these clocks are not connected by a solid body, since we already know that bodies change their sizes depending on the velocity in the environment. That is, in the supposed light-bearing environment the speed of light is constant relative to the environment, but the light between moving bodies in this environment will have a different time of passage back and forth between them, because in one case the body is running away from the light propagating to it, and in the other case, moving towards it, so the apparent speed of propagation of light in different directions between bodies will be different. This apparent speed of light propagation between bodies is called the one-way speed of light. The time of light travel between bodies will depend on the angle between the direction of light propagation and the direction of motion of bodies relative to this environment, as well as on the value of the velocity of bodies in the assumed environment. For better accuracy of measuring the time of light travel, it is desirable to use large distances between clocks, and this is possible if we place the second clock in space and have the first clock on Earth. The second condition for determining the one-way speed of light is that the angle between the propagation of light from one body to another and the vector of velocity of the bodies relative to the environment changes. This is possible when the bodies are involved in mutual rotational motion. Such mutual rotational motion, taking into account the above-mentioned, can be pairs of bodies, the Earth, the Moon, the Earth, a satellite in geostationary orbit, two satellites in geostationary orbit, two satellites of any navigation system, GLONASS, GPS, BEDA, and the like, in one orbit, any pair in the supposed space project on measurement of gravitational waves, LISA, and the like. The most accurate measurement would be a system consisting of a pair of bodies of the LISA project, but this project is in the distant future, so realistic can be considered the location of clocks on the Earth and on a satellite located in geostationary orbit, or on two satellites of some navigation system, especially on such satellites are already installed clocks of high accuracy. We will describe the proposed experiment for the system of clock arrangement in the laboratory on the Earth and in the geostationary orbit, as it is easier and more illustrative to describe it because of the constant distance between the two clocks and the expected higher accuracy of the laboratory clock on the Earth. To explain the idea behind the experiment in general and clock synchronization in particular, consider the figure. Assumes that the laboratory and the satellite have television cameras that broadcast images to each other, with the cameras showing their own clocks and a monitor, and the monitor displaying the image from the other camera. For convenience and clarity, the clock in the lab has a round face and the clock on the satellite has a square face. The figure shows the image that can be seen in the lab on Earth. This image shows the round clock on the right, which shows the time in the lab, and the monitor on the left, which shows the image from the satellite camera. On it the image of their clock in a square frame and their monitor, on which came the image from the laboratory, where you can see the image of our clock and the image on our monitor. Actually, there will be many such diminishing images and their number depends on the resolution of cameras and monitors. But it is enough for us to see two images of our own and other watches. So, if the difference between the readings of the laboratory clock, round, which is shown on the image as T1, and the clock, square, from the satellite, shown as T2, are equal, then it means that the clocks are running at the same rate. If the rate of the clocks is different, you can adjust the laboratory clock to match the satellite clock. To synchronize the laboratory clock with the satellite clock, it is enough to set the time on the laboratory clock equal to the time of the satellite clock, which is currently displayed on the monitor, plus half of the time difference T1. The essence of the proposed experiment to determine the one-way speed of light is that if during the day the difference between the readings of the clocks in the laboratory and on the satellite will change in the form of some return oscillation, it means that the speed of propagation of the radio signal between the clocks will vary depending on the direction of its propagation in space. If the difference of the clock readings will not change, it means that the speed of propagation of the radio signal, light. Experiment description. We can propose the following variant. There is a receiver on the satellite that receives some signal from Earth, in which is encoded a moment of time, called the epoch in navigation systems, by which the time of its clock is read. This signal is amplified and sent back and changed to Earth. This signal return is necessary to control mutual velocity by the Doppler effect and to determine the distance between objects. Then the counted time of the satellite's clock is sent to Earth through some communication channel. In the laboratory, by the same encoded moment of time in the return signal read the time of its clock and immediately sent a new signal to the satellite, and such an exchange of signals occurs repeatedly. Taking into account the delays in the laboratory and satellite equipment, it is possible to construct time intervals similar to the still frames of a video camera, but with several orders of magnitude higher accuracy. Clock adjustment, clock synchronization, and time interval analysis for determining the one-way speed of light is the same as described above for still images of video images. If a periodic change in the difference of the clock rate during the day is detected, it is necessary to determine the average difference of the clock rate for a day. For absolute synchronization of clocks, it is necessary to set the laboratory clock so that at reduction of their readings by the average difference of the clock rate for a day, the difference of the rate of one clock was symmetrical with respect to other clocks at apparent wave shifts of their readings. That is, at primary synchronization of clocks, they are synchronized by the average time of signal motion back and forth, at that synchronization is carried out at random direction of signal propagation to the velocity vector in the environment. And at absolute synchronization of clocks, it actually leads to synchronization at mutually perpendicular direction of signal propagation to the velocity vector in the environment. Calculation of the magnitude of the expected effect. Let us evaluate the possibility of detecting the value of the one-way speed of light in the described experiment. For this purpose, we set the following expected parameters. We take the expected accuracy of the clock on the satellite to be 10 to the minus 12th degree, which gives a daily error of 86 nanoseconds, and we assume the accuracy of the clock in the laboratory to be an order of magnitude higher, so we do not take it into account. We take the speed of light equal to 300,000 kilometers per second. The distance to the satellite in geostationary orbit is almost 36,000 kilometers. We take the expected velocity relative to the environment to be equal to the average velocity relative to the microwave background radiation according to the Planck space project, which is about 368 kilometers per second. The angle between the ecliptic plane, in the plane of which the satellite rotates, and the vector of motion of the Sun relative to the microwave background is small, and we will not take it into account. This vector is directed toward the zodiacal constellation Leo. The speed of the Earth's orbit around the Sun is about 30 km per second, and we will use it in calculations as the minimum speed relative to the environment. The calculation is carried out in the program LibreOffice CALC, similar to Microsoft's Excel. The results of calculations are presented in the table. The data in the table are rounded. Analyzing the results of calculation. Analyzing the results of calculations presented in the table, we can draw the following conclusions. Clock readings during the day can differ, both in one and in the other direction, by 286 microseconds for the velocity in the environment equal to 368 km per second, and by 24 microseconds for the velocity in the environment equal to 30 km per second, which is more than 3,370 times more than the error of the daily rate of the satellite clock. Therefore, it is possible to detect and determine the magnitude of the one-way velocity and its direction. If the velocities in opposite directions between the clocks are determined, it will not be difficult to calculate the speed of light relative to the environment. We will not assert in advance that it will be so, but the logic of the previous reasoning points to the possibility and even necessity of such an environment. At least it is worth to conduct the proposed experiment to confirm or deny the dependence or independence of the speed of light on the direction in space. I want to emphasize that we determine the dependence not of the two-sided speed of light propagation in space, but of the one-sided speed of light propagation. That is, if a daily difference of a course of hours, synchronized by the offered way, will not differ more than the established error, the one-sided speed of light is equal to two-sided speed, and it will confirm a postulate of the special theory of relativity. However, in the case of periodic difference of a course between clocks, we can calculate by results of the offered experiment to determine true speed concerning the supposed environment. Options for implementing the experiment. 1. To install on the next launched geostationary satellite repeater the necessary additional equipment, which will have a small mass, using temporarily part of the regular equipment, such as power supply, receiver, transmitter, antennas, stabilization, and orientation system. 2. Use a Chinese Beta navigation system satellite, if it is still alive, in geostationary orbit, which already has an accurate clock and all the necessary equipment. 3. Use 2 satellites in geostationary orbit to place clocks on them, doubling the distance between clocks and eliminating ionospheric and other interference from the Earth. 4. Use 2 satellites of any of the current or newly deployed navigation systems in the same orbit, which are far apart and have minimum mutual relative velocities. The advantage of such a system is that all necessary equipment is available on these satellites and the clocks on the satellites are in the same conditions.
Of course, it is possible to try to use, as a second clock, the satellite clock of any existing or newly deployed navigation system, but such an experiment will have a lot of disadvantages that must be compensated somehow, and there can be several variants of such compensation for each parameter, depending on what theoretical ideas we use in this case. We can mention several such disadvantages: the presence of relative motion between the clocks on the Earth and on the satellite, and the change in the distance between them, the departure of the satellite over the horizon with the impossibility of observing it during the entire experiment, that is, during the day. It is not clear how to synchronize the clocks correctly in the case of the presence of mutual speed of the clocks, and whether the course of the clocks changes depending on their relative speed. Therefore, such an experiment will be, if not absolutely reliable, then at least doubtful. The system of placing the second clock on the Moon will have the same disadvantages, which are hardly compensated by a much larger distance between the clocks.
The best options for realization of the experiment. It can be expected that the use of a pair of satellites of any navigation system in the same orbit will be the cheapest variant of the experiment. One should not exclude the use of a commercial satellite in geostationary orbit with an additional module, which can be the simplest and best option if we use this data to improve the performance of the whole system. And the use of 2 satellites in geostationary orbit with additional or full-fledged modules can be considered an almost ideal variant of the experiment realization. Conclusion. The proposed experiment to determine the one-way speed of light is technically feasible, simple, and the cost of its realization will be relatively small. The proposed method of clock synchronization allows synchronizing the separated clocks both by the average time of the signal movement back and forth, as well as to carry out absolute synchronization of clocks. According to the results of the proposed experiment, it is possible to determine the following: the unilateral speed of light in both one and opposite directions, the speed of the clock relative to the light-bearing environment, the speed of light propagation in the light-bearing environment. The results of the proposed experiment are important not only for practical use in space navigation, but they are even more important for fundamental physics. To you, the viewers of this video, please make sure that this information reaches those who can contribute to such an experiment, or at least it reaches more viewers. This is the end of the video. But this is not the end, but the beginning of the next, new and, hopefully, even more interesting one.